and welcome to this video on forces, specifically balancing forces and force calculations. A recent article from Healthline tells me that in order to bench press a barbell, the average person can bench press 135 pounds. What force would a person need to apply to make this happen? So what we want to look at here is we want to be able to calculate what force. And while it seems very difficult, we'll start with the simple problem and start building our way up to the more complicated ones. So let's start by talking about this. You want to apply a force to a barbell. What is the object of interest? Well, in this case, it's a barbell. Once you've done that, the same problem-solving strategy we've been using all year of the go-guess method still applies. First, we have to draw a graphic organizer. In this case, our graphic organizer will always be a free body diagram. To say that again, for a force problem, your graphic organizer will always be a free body diagram. We're talking about a bench press, okay? We're talking about lifting a barbell. That's our object of interest. So what forces are acting on our barbell? Well, we think about lifting a barbell. You push up, and is there anything else really touching it? Well, you might have a spotter, but we're going to neglect that for this problem. So it's just you and the barbell. So you apply a force upward, and gravity pulls it down. The next thing we have is our givens. What are we given? Well, the only number we're given is this 61 kilograms. And we want to find out what force we need to apply. What force do you need to apply? What's the applied force? This would be a mass. So this seems very sparse, very problematic, but at its barest bones, this is a very easy problem because we've already solved this. We know that in order for an object to stay in motion, the forces need to be balanced. If you want to think about it, taking that idea and translating it, in order for you to be able to lift a barbell, you
have to overcome force gravity. According to Newton's first law, an object in motion will stay in motion and an object at rest will stay at rest unless acted on by an outside force. In this case, the object, or the barbell, will continue resting on the floor until such a point that there's enough of a force to provide it with an upward velocity. Once you have that velocity, all you need to do is match force gravity to maintain the upward velocity. But to get it going, you need to overcome it. For this problem, what we're going to do is calculate what the force we need is to keep it moving upwards, or the force we initially need to overcome to get it moving in the first place.
In order to lift your phone, you need to overcome the force gravity. Now, a barbell is slightly heavier than your phone, but we still need it. It's still the same idea. This force applied needs to at least match this force gravity. Thankfully, we have an equation for that. In many instances, or many of the instances we're going to talk about, the equation for a force problem is the sum of all forces equals mass times acceleration. Now in this case, instead of leaving it here, we're literally going to list our forces. We're only talking about up and down, we're only talking about the y direction, so we're only going to pay attention to y right now. But I'm going to put that label on for later. And so instead of stopping here, we're going to literally list our forces. What are my up forces, my positive forces? What are my down forces, my negative forces? So in this case, applied is up, so I'm going to treat that as positive. So a force applied. Again, arrows are strictly important, but you can leave them out for now. Minus, because gravity is going down, force gravity. They are opposite
in direction.
They will balance each other out. There are two schools of thought here. I put a negative sign so that way I can just focus on the numbers later. I get the negative sign from the drawing, from the free body diagram. Down is negative, up is positive. There are plenty of people who would say just list them all as positive, add them all together. You'll add the negative signs in later. Each to their own. I personally recommend adding it in here so that way you can focus on just the numbers later. Once you have this, we can start filling in numbers and some assumptions. If you're going to lift this, we need to know what force we need to apply. We always assume the minimum force. We assume that we have to use at minimum this. In other words, we need to make sure at minimum this acceleration is 0, not negative, pulling us down. So typically, when told what force do you need to apply, what force do you need to overcome, you're going to go, what is the minimum value that would make this work? Especially if there's no acceleration mentioned. So we can assume in this particular case, the acceleration is 0.
Because we're looking for what force do we need to lift it, we're looking for the minimum amount of force. We're looking for the point where the forces are balanced, which is to say we're looking for when the acceleration is 0. That's how we know the acceleration in this instant is 0.
We don't know our force applied, that's our unknown, but we also don't know our force gravity. And that's a small problem, except we have an equation for force gravity, and that equation is force gravity equals m times g. In this case, I can do mg, at which point I can go, okay, well 0 equals force applied minus 61 times 9.8. Or in other words, in this particular case, my force applied is 597.8 newtons. And that's fairly self-explanatory. That's fairly simple. So let's step it up a notch. Okay, let's take a look at another example. In this case, you and your friend are asked to move a heavy table across the house. If the table has a mass of 45 kilograms and your friend applies a force of 200 newtons upwards, what force do you need applied to keep the table in the air? Again, we're looking at the minimum amount here. We're looking, okay, how hard do you need to lift to keep this table off the ground? And again, we'll start with a free body diagram. So in this case, you're lifting a table. You're paying attention to the table. Wondering what force you need to apply. But your friend's also lifting in this case. So there's going to be 2 force applieds, one for you, one for your friend, and we don't know what their values are. There's also going to be this force gravity pulling it down. And the process isn't any different. Your friend is applying 200 newtons of force. We know the 45 kilograms, so we can find the force gravity. The only difference in this particular case is that you have 2 forces going up. So when you do sum of all forces equals MA, you're going to add your force applied and then your force applied of your friend. Maybe you designate F or 2 to tell them apart, but do make sure you tell them apart somehow. And then you're going to have the force gravity pulling down. Everything else is still the same idea, it's just we're adding multiple forces. So in this case, you're just keeping it off the ground, your acceleration will still be 0. Your applied force is what you're finding, your friend's force is 200, and your force gravity comes from the equation.
Why don't you go ahead and find how hard you need to lift?
Okay, if you follow the math through, you plug in mg for force gravity, you plug in the 200 for how much your friend's applying, and you follow the math through, you get that you need to apply 241 newtons. You're doing more of the lifting here, but only barely. But the process, the math, isn't that difficult. At least as long as we're going in one dimension, up, down, left, right, but that's not typically the case. Very rarely are we talking about just up and down forces. Typically we're talking about objects moving, sliding left and right. So let's take a look at one of these kind of examples. So here we have another problem. You're asked to move the leather bottom chest across the wood floor of your grandmother's house. The chest has a mass of 62 kilograms. How hard do you need to push against the chest to get it moving? It's the same general problem. The only difference here is you're pushing on a chest.
More specifically, you're pushing in the x direction.
So let's draw a free body diagram for this really quick. A chest is resting against the floor. You're not lifting it, we're pushing on it. So if it's sitting on the floor, it's going to have gravity pulling it down, which is kind of constant, always there. You have the normal force pushing it up, stopping it from falling through the floor. You're going to push it this way. And the final force we're missing is the frictional force, which is trying to stop it from moving. And the question here is, how hard do you need to push on it to get it moving? What's the minimum amount of force you need to apply? Or in other words, how hard do you need to push on it to overcome the frictional force? With that said, what we need to talk about is two things. Number one, we have two directions. We're not just up and down anymore. We're up, down, or left and right. And number two, what type of friction is this? We'll start by talking about number one. In number one, we have two directions, up and down, left, right, which at this point should be fairly obvious that we're going to split it into two parts, one for x, one for y. So when we do our sum of all forces, we only care about forces acting in the x direction. So my sum of all forces in the x direction is equal to my mass and acceleration in the x direction. If I look the x direction left to right, the only things are applied and friction. Applied's going one way, friction is going the other. They oppose each other. If I do the same thing for up and down, sum of all forces in the y direction, MAY. What's going up and down? Well, normal and gravity. Normal's pushing up, gravity's pushing down, so normal will be positive, gravity will be negative. The follow-up question is, what type of friction? You're pushing on it and you're trying to get it to move, which means it's not moving yet. It's standing still. It tells you that this will be static friction. So from here, you want to find your force applied. Let's go ahead and fill some things in. It's not moving yet, so we know my acceleration is going to be 0. And my acceleration is going to be 0, both up and down and left and right. I know that force gravity is going to be equal to mg, but I don't know much else. I mean, you can put in the formula for friction, but I don't, well, I know mu, or I can find it from this table. I don't know Fn. But wait, Fn's over here. I can find Fn this way. And so what we get is a simple system of equations. By solving in the y values up and down, we can then solve the x values. Again, you can do this symbolically and say that, well, in this case, Fn equals mg, and then take that value and plug it in. Or you can literally say Fn equals 62 times 9.8. Symbolically or the such, either way works. I'm going to continue on symbolically for the moment. In this case, Fn is m times g, so anytime place I see Fn, I'm going to plug in mg. So 0 equals force applied minus mu s times mg. And I can get my force applied that I need to push in this particular case, is mu mg. For those of you who did a number, you're going to get the 62 times 9.8, plug it in. Regardless of how you do this, in this case, we'll get the leather wood from right here, 0.61 times the mass of 62 times the 9.8. Put all that together, and you get 370.64 newtons. And that's how hard you'll have to push to get it moving. Again, the problems are fairly simple. It's the same general process. What is your acceleration? What is your x? What is your y? Let's look at one more. Okay, here we are continuing on. You're asked to move the leather bottom chest across the floor of grandmother's house. Wants to get the chest moving. You need or want to get this over with as fast as possible. If the chest is still 62 kilograms, what force do you need to push on the chest to produce an acceleration of 1.2 meters per second?
Squared.
All right, so this one's different because we have an acceleration. We have a rate that it's going to increase in speed. So let's set this up together, and then you'll try it out on your own. So again, start with the free body diagram. You have the normal force You have gravity. You're pushing on it. But in this case, the frictional force isn't going to match. You have an acceleration, so your force applied has to be bigger than your frictional force. As a follow-up, we also know that we're moving this time. We are moving. So this is going to be your kinetic friction. The rest of the problem is fairly
similar.
You're going to have an X. You're going to have a Y. The equation's still going to be your sum of all forces equals ma, and then you're going to add your forces. And the same thing over here for the y direction. Add your forces. The coefficient of friction is given to you. It's going to be the kinetic value, which is this one. The only difference here is that your acceleration is 1.2 meters per second squared. It doesn't say which direction that acceleration is, so we need to stop and think. When you push on a chest or a table or really anything, you push across the floor this way, which way would the acceleration be? Is it going to be up and down, or is it going to be in the x direction? Once you've figured that out, go ahead, solve the problem the rest of the way through, find how hard you need to push. Go ahead. Okay, let's give this a try. We start over here with our acceleration in the y direction being 0 because when you push on something, it goes in the direction you're pushing, which means the 1.2 is in the x direction. Y, it's not going to fly up into the air or down into the earth. It's going to stay constantly here, which means your acceleration in the y direction is 0. I use this to solve for my Fn, get my Fn. This time I got a number just for contrast, and I take it and plug it in over here for my Fn. I use the kinetic friction because I'm moving, so the 0.52, and this time it doesn't equal 0, so your force applied won't directly equal your force friction, it'll equal your net force, or the difference between these will equal your net force. So I get 62 times 1.2 equals force applied minus 0.52 times 607.2. Do that math, I get 390.35 Newton. Let's clean that up for you really quick. 390.35 newtons. There you go. Have a good one. Thanks for watching.